from here, Azaric University, Brno, we'll talk about principal pairs of quantum homogeneous spaces.
Thank you for the introduction, and I wish also to thank the organizers to give me the chance to give this talk and also make a bit of an advertisement for the topics of next week conference in Prague. So also today I'm going to talk about a working collaboration with Ramon, which is this notion of principal pairs of quantum homogeneous spaces. As I shall repeat in a minute, this work concerns the problem of constructive quantum principal bundles in the setting of non-commutative geometry, which usually is not a trivial matter, but we found some nice framework in which this can be done easily. So let me remind, since the crowd here is merely composed of classical geometry, let me remind what is the point of view or the starting point, if you like, of non-commutative geometry. Everything takes the move from the idea of substituting spaces with functions. Or to be more formal, everything starts with from the celebrated Gelfand-Naimark theorem, which establishes a contravariant equivalence of categories between locally compact Ardour spaces and commutative sister algebras. So roughly speaking, one can take any geometric objects and translate any definition, any theorem, in commutative sister algebraic sense. Commutative sister algebraic language, I should say. And this is a contravariant equivalence, so I have two reverse arrows, because every time that I have a map between two spaces, I have a map that goes the other way around from the algebra of continuous function of the second one to the algebra of continuous functions of the first one by pullback. So the next step to talk actually about non-commutative geometry is to forget about commutativity and keep on doing this job of translating geometric objects into algebraic ones, and thinking of this as thinking of sister algebras, non-commutative sister algebras in general, as algebras functions of non-commutative spaces, which sometimes are also called quantum spaces or virtual spaces or whatever. So the natural question for us that work in Lie theory is what is, in the light of Gelfand-Naimark theorem, a compact Lie group. It turns out that in this case, we can forget about all the sister algebraic subtleties, and we can just be happy of working with the algebra of representable functions of a Lie group, which has a nice algebraic structure. It is in fact what is called an Hopf algebra. Then one can complete everything with the suitable topology and let the sister algebraist dot the E and trace the T's. So the structure that we look at is a so-called Hopf algebra, what is an Hopf algebra? It is a quadruple of, an algebra, a unital algebra in fact. This map that is called the coproduct, that goes from A into A tensor A. This map that is called the antipod, or sometimes in older paper, the co-inverse. And this map that is known as the co-unit. So as I said before, when we look at the algebras, we have to reverse the arrows, and in fact, the coproduct goes in the inverse way of the product, while the co-unit goes in the inverse way of the unit if we think of the unit of a group as an homomorphism from the one-element group into our group. Moreover, in order to have something that is actually describing a group and not some random algebraic structure, we have to add the good axioms. So we have this list of 3 axioms that describe completely an Hopf algebra. And okay, maybe if you look at them written in this way, they are not so enlightening, but if later you go back home and you try to draw the commutative diagrams, you will find out that you have drawn the commutative diagrams that describe the axiom of a group, only again with the arrows that are reversed. So it's in this context that one can talk about so-called quantum groups, as we shall do in a moment, and also to describe the corresponding notion of homogeneous spaces that we call quantum homogeneous spaces, and we can in fact also talk about vibrations. And let me just say that there is no common agreement on what we can consider as a vibration in non-commutative geometry in the general sense. We have a very strong notion of what is a quantum principal bundle, but it costs a lot of sweat and tears to go beyond there. And nowadays we have a good notion, or at least some good proposition of a notion of a quantum fiber bundle where the fiber is an homogeneous space. So
that should be SU3.
that should be SU3, yes. Sorry. Yeah. So this effort was this program was started in 2002 by Bonecchi, Cicco, and Tarlini, and they were interested in describing the quantum twistor bundle as a quantum fiber bundle over the force sphere, the quantum force sphere. And then, almost 20 years later, Brzezinski and Szymanski presented an example of a vibration where the fiber is the so-called Podlesh sphere. And then 1 year later, they gave a general framework to describe this kind of vibrations, where again, the fiber is now a quantum homogeneous space. And what they did was to generalize the framework of Galois extension, which is the framework in which we describe quantum principal bundles. So today, as I said before, I will not talk about the whole theory of Brzezinski and Szymanski, but I will talk about a simple and effective framework in which we can produce examples of non-commutative vibration, both principal and non-principal, starting from a nested pairs of quantum homogeneous spaces. I will define every object in a moment. So the picture, when we deal with non-commutative geometry, it's a good habit to have in mind the classical picture that we're trying to generalize. And the classical picture that we had in mind is this one. So I start from some group G, and I have two subgroup N and then inside of G, which are disposed in this telescopic way. So we naturally have a fiber bundle given by the vibration of the bigger homogeneous space on the other. But this bundle is in general not, as you know, is not a principal bundle unless one make one specific request, that is N should be normal inside of N. In that case, we got a principal bundle where the typical fiber is the group M over N. Nothing incredible here, of course. So, as I said before, the setting to generalize this particular situation is given by off-Galois extension. So let me tell in a moment, in one slide, what are off-Galois extension. If I start from a comodule algebra, and if you don't know what is a comodule, again, take your familiar notion of a module of a group and invert all the arrows, and you get what you will call a comodule. So we start from a comodule algebra over an off-algebra A, and we say that it is an off-Galois extension of the space of its coinvariance if I have a bijection given by this canonical map. So this, in a way, this is the non-commutative version of the fact that I have some local trivialization. So a principal right-edge comodule algebra is just a right-edge comodule algebra that it is an off-Galois extension of the space of its coinvariance, and we have to require this homological additive property that it is faithfully flat as a module over the space of its coinvariance. One particular example of this construction is given by quantum homogeneous spaces. So let's start from an algebra A, and we take some left coideal subalgebra, and we require, moreover, this technical condition, this commutativity between B plus A and AB plus, where the plus here is the intersection of B with the co-unit map of A. Then we can consider this quotient map, and as a matter of fact, this guy here, A over B plus A, is an algebra. We have a coaction of this algebra on our original algebra A, and it turns out that our left coideal subalgebra B is the space of coinvariance of this coaction, and we call B a quantum homogeneous space of A. Let me stop for a minute because I want to give you all the correspondences, classical quantum here. So here, ideally, you should think of A as the space of function of a Lie group, or of a group, I guess, in general. And what B is, of course, will be the space of a function on the homogeneous space that I'm describing, while pi B of A is describing the isotropic subgroup of the space described by B. So this is the setting that you should keep in mind. So from now on, I will consider pairs of homogeneous spaces, and just to save words, I will say that B inside of P, two quantum homogeneous spaces, are a nested pair of homogeneous spaces, or just a nested pair. Moreover, if we require that pi B of P is an algebra itself, this means that pi B of P is in fact describing a group, and this corresponds to the fact that we have a normal subgroup, which justify the definition that we gave. A principal pairs of quantum homogeneous space B and P is given by these inclusions, B inside of P inside of A, and we require that the projection onto the smallest homogeneous quantum homogeneous space, restricted to this intermediate guy, is an algebra. Of course, this must not be the case always. It can happen that this can just not happen in some specific cases, just like not every subgroup of N has to be normal inside of it. So, however, even when we have this inclusion, B inside of P, we have some attractive algebraic properties that lead to some interesting non-commutative geometry. So first of all, P is faithfully flat over B. Moreover, for those who know, what happens is that the components of Takeuchi equivalents are right pi of P of A commodule maps. Hence, we have an equivalence between, what happens is that we have an equivalence between the category of relative AB module with right pi P of action and bicomodule pi B of A by P of A. So all of this, we used all of this material to prove that we still have a canonical isomorphism, but now the canonical map is not anymore an isomorphism between the whole of A. Okay, we still have it, but because we have a, what happens is that the isomorphism between A tensor A and A tensor pi B of A restricts to an isomorphism where when on the left side we have to take P tensor P, and on the right side we have to consider this potential product that is just a subgroup tensor product of A and pi B of P. So together with faithful flatness, this allows us, from a non-commutative point of view, to think of these objects as non-commutative fiber bundles. In fact, they fall in the domain of Brzezinski and Szymanski theory for non-commutative fibration with fiber that is a quantum homogeneous space. And we think of this triple of algebras, B inside of P and the space of the covariance of POA with respect to the coaction of the smaller quantum group as a non-commutative fiber bundle with a quantum homogeneous fiber. Concretely, let's see some example from Dreamfeld-Jimbo quantum groups that were described yesterday by Raymond. Let me remind you what these guys are. We start from a complex semi-simple Lie algebra G, and we have the associated compact connected, simply connected Lie group big G. And from the literature in mathematical physics of the 80s, we know that we have a pairing of two one-parameters family of algebras, one quantizing the enveloping algebra of the Lie algebra G, and one quantizing the coordinate algebra of the Lie group G. And as Q goes to 1, we can recover the two classical objects. Moreover, all the classical representation theory carries over, and we have a good notion of highest weight representation for these objects. So, in a way, we can think of these objects as we can continue to use the classical representation theory of compact Lie groups when thinking about Dreamfeld-Jimbo quantum groups. And in fact, we can make a construction of flag manifold, of quantum flag manifold in this case. So what we do is, to do this, we take a quantum Levy subalgebra of UQ of G, that is, we crossed out a certain number of nodes from the linking diagram, and we throw away the E's and the F generators of UQ of G corresponding to those nodes. And in this way, we get a Hopf subalgebra of UQ of G, and we can look at the space. So since we have a left action of UQ of G on the quantum coordinate algebra, we can look at the space of covariance with respect to this left action. And we call this guy the algebra of function, or just the quantum flag manifold OQ of G over LS. Yes, and this is what I was saying before. We represent OQ of GLS just by crossing out any subset of nodes of a Dinkin diagram, and this graphical representation will in fact be useful in a moment. So, to describe principal pairs, to describe nested pairs of quantum homogeneous spaces in this context, I can do just the following. We consider any subset of cross nodes of the Dinkin diagram, and we have this triple of algebra. Then we have an isomorphism of this last guy with the Levy subalgebra where of LS of B, where I have removed the guys that are in common between these two subsets of nodes. In other words, we can just describe non-commutative vibrations in this context by looking at Dinkin diagrams, and we can start by considering the example introduced by Brzezinski and Szymanski. They were considering the Dinkin diagram corresponding to the full flag of SU3, and as a base one has the color Dinkin diagram of quantum CP2. Now what is left here, if I just oppose this diagram to this second guy, is the Dinkin diagram of the Podresh sphere. So here we can describe, according to this picture, we have described a quantum vibration where the base is given by quantum CP2, and the full space is the full bundle is the full flag of SU3, and the typical fiber is S2. But there is no reason to restrict ourselves to this example. In fact, we can think of generalizing it by looking, first of all, to the case in which one goes one rank up and considers the full flag of SUN in general. And again, now as base we consider quantum CPN. And this gives us a vibration when the total space is the quantization of the full flag of SUN, and the base is quantum CPN, while the typical fiber is given again by quantum full flag, but one has to go one rank below. Or, and this is just to show up that one can play around with linking diagrams and produce many examples of non-commutative geometries. We can choose to just color to generalize this guy by just coloring the two extremal nodes. In this way we got this flag manifold, and again the base is given by quantum CPN. And here we are describing a case in which the fiber is given by the quantum projective plane of rank -1. Just to have fun, we were considering also a case in which one has the base given by the octagonal plane, and the typical fiber is the 5-dimensional sphere. So I hope I conveyed the message that here one can stop of taking care of all the particular homological properties that define a vibration with homogeneous fiber and just play around with linking diagrams. And this is what I said so far was for the general case of a nested pairs of quantum homogeneous space. But as I told you before, we can consider instead the case in which the restriction of the projection of A onto the quotient of A by B plus A is itself an Hopf algebra. Well, if I restrict this guy to P, I get an Hopf algebra. In this case, we get some extra features, and in fact, we will get some extra non-commutative geometry. So first of all, this coaction restricts to a coaction on the middle guy. And the space of coinvariance with respect to this coaction is again the base quantum homogeneous space. What happens is that this pair in fact gives a principal comodular algebra, and we have again an equivalence of categories between relative A-B modules and relative A-P modules with a right phi B of with a coaction of this Hopf algebra. We use this fact to prove something about quantum principal bundles. So far I have described what in non-commutative geometry we call, well, principal comodular algebra or non-principal comodular algebra. But to describe a full-fledged quantum principal bundle, we should give in fact some information about the referential structure. And in general, it's quite difficult to prove that one has an ATIA sequence that gives you a quantum principal bundle. But for this setting, if I have a principal pair B inside of P, so I also require that this guy is an Hopf algebra. And if I have a first-order differential calculus that is left A covariant and is right covariant with respect to an action of pi B of P, then it tells that this pair P omega 1 of P gives a quantum principal bundle. So we have a way to produce quantum principal bundles, but just by checking coinvariance conditions on my given first order differential calculus. So our motivating example was the pair given by a reducible quantum flag manifold and the corresponding quantum Poisson homogeneous space. Why the reducible quantum flag manifolds? Because these guys are the ones for which we have a good calculus, that is a good first order calculus, that is the celebrated Eigen-Wegener code calculus. And what happens is that these pairs always give a principal pair. Here, pi B of P is basically U1. These guys are all products of U1. These guys are basically U1 bundles. And yeah, that's what I just said. And we get a quantum principal bundle given by the pair of a quantum Poisson homogeneous space and the corresponding Ekeberger Kolb calculus. And in fact, we use this, okay, so just a moment of self-promotion, we use these factors to prove Borel-Weil theorem for irreducible quantum Flagg manifolds. Okay, let me finish by telling you something about differential structure in the non-principal case. So again, we are again dropping this condition that pi b of p is an off algebra. This is still a work in progress with Riemann, but what happens is that at the level of the universal calculus, we got something that really resembles a Mathias sequence. So if I have, again, B inside of P, a nested pair, we have this universal short exact sequence, but as Raymond told you yesterday, we don't get much information from the universal calculus of an algebra. We would like to describe something more geometrical. So, and I get any differential calculus over B by quotienting out by some good subcomodule of the universal calculus, and so it's for omega 1 of P. So we define a differential nested pairs of quantum homogeneous space as a nested pairs together with a subobject inside of the universal calculus of the middle guy here, which is in the right category. So the category of P bicomodules, which emits a left A coaction, but we also require to have a right pi B of A coaction. In this way, we can take the quotient of this short exact sequence, and we can generalize the notion of a quantum principal bundle to the notion of a quantum bundle where the fiber is a quantum homogeneous space. We wish to create more examples of these objects, in particular the rule of the calculus in the middle could be played by the calculi that Raymond was talking about, constructed using the PBW basis, the stick root vectors, but this is a story for another day. In the while, thank you for your attention.
Question?
Can you say something about quantum symmetric spaces?
No, not really. Like quantum symmetric spaces are a completely different theory with respect to quantum.
Why? Why different? Completely different.
Sorry?
Why completely different?
Because when you try to give some quantization of a classical symmetric space, you end up with something that doesn't enjoy
but
this.
you have projective spaces, so you have very degenerate.
Yes, you can describe projective space.
And for full flags or for, say, for Grassmannians.
So we have irreducible quantum Flagg manifolds are very special in the sense that they are both quantum Flagg manifolds and they are quantum symmetric spaces. But okay, all the theory that I have described so far is what they inherit from being quantum homogeneous spaces. For what happens with quantum symmetric spaces is that we don't have a good notion of this guy here, the alpha.
Sorry, you have no good notion of what?
Of the quantum version of the isotropy subgroup. It just doesn't work. People, you have to invent something else. And
there is a more general construction than the Podlej spheres. There is a construction of Gurevich and Donin and Haroshkin of quantum orbits.
Yeah, I know. I'm just saying that I am not very aware of it. I know that it exists, but I'm not an expert in quantum symmetric spaces.
Because it's just these Podlesh spheres, they are just a very small example.
Of course.
But there are also quantum
There are two parameters.
alloys and higher dimensional analog of these quantum orbits.
Absolutely, absolutely. In fact, there are the same constructions also for the other irreducible.
It should work, in principle.
In principle, it should. How to make it work, I don't know.
Yeah, it's just the position for the non-standard published
Yeah.
Okay. Any other questions? No, let's thank you.